Alrighty, well, I think we're good to begin. Thank you to everyone who came out today to see our guest speaker.
Okay, Chris.
Just real quick, I'm going to go over some the agenda for this meeting and some basic Zoom etiquette. This event will last from 6 to around 8 p.m. We'll probably get out a little bit before that. This just allows our guest speaker to speak for about 90 minutes. And then that way we have about 30 minutes at the end to do a Q&A session. Throughout the presentation, if you can just keep your microphones muted, so that way we don't disrupt our guest speaker. It's not required, but it is encouraged if you are okay with it to have your face cam on, just so there's a little more interaction between the audience and our speaker. We greatly appreciate that. And then once the Q&A session comes around, obviously you can unmute yourself and ask questions. That is encouraged at that time. If you don't feel comfortable asking questions, you can use the chat function. Just keep in mind, myself and Jose will be reading it, and so that way our guest speaker doesn't have to be worrying about that. And yeah, we just ask everyone, please be respectful. Try not to interrupt our guest speaker. And yeah, it should be a great presentation. Stop sharing this now. So I'll go ahead and introduce our guest speaker for today. Today joining us is Dr. Richard Dick P. Hallion. I can say a lot about this gentleman. He asked for a shorter introduction, so I'll try to keep it short. He's currently an AIAA fellow and part of the Distinguished Lecture program, which brought him out here today. He has a long history in the aerospace community, both as a policy analyst. He's worked at many different universities and museums throughout the country. He is also an author. He's written 13 books. So very distinguished there as well. And he's currently working as a research associate in aeronautics at the National Air and Space Museum at the Smithsonian Institute. Today he'll be giving us a general overview of the history of flight. And if he's ready, I'm going to pass it over to him now.
Okay, thanks very much. Let me fire this sucker up here. And we are, I think, good to go. Let's see. There we go. Great. Well, it's a real pleasure speaking with you all, and Dylan and Jose and the rest of you that are on the line. I've always enjoyed, as a member of AIAA, dealing with the student branches. I was active in the AIAA student branch at the University of Maryland myself back in the 1960s and early 1970s. And it's a wonderful, wonderful operation for grooming you and getting you into the aerospace world. AIAA is an organization that I'm very proud to be a member of. They have a number of initiatives that they're really increasing, I think, in terms of outreach to younger people. And we certainly need that, because a bunch of the old timers like myself, we're moving very, very rapidly off the stage. We think of things like airplanes and conventional spacecraft and stuff like that. And you folks and your predecessors are already taking us in many, many different new areas. You look at the integration of cyber, some of the things we're seeing with drone technology, some of the ways we're seeing the application of advanced aerospace to the privatization of space, to urban mobility, things like this. These are things that people like myself considered science fiction, and it shows how dynamic our field is, and the fact that all of you, I think, are going to have a great deal of pleasure working in this field in the years ahead. Number of challenges, but a great deal of pleasure certainly working in it as well, and particularly in the state of Florida, where we are, of course, front and center in the whole spaceflight revolution, and have been for many years. When you take a look at Florida as one of the planet's launch points to the stars, that's really quite impressive. When you think of human history and where you are going to be playing in that field. So today, what I'm talking about is actually really two revolutions that started at mid-century. And that was the transition from basically flying below the speed of sound to flying above the speed of sound. And then moving beyond that into an area that we're very cognizant of today, and that's the area of hypersonics. And so if we start out, we can take a look at a kind of traditional progression chart on aerospace technology. You know, people are always fond of plotting Mach number versus time, and you come up with a curve that's basically like this. This takes it up through the speed of sound, through the fulfillment of flight into the Mach 3 regime. And, you know, it's your typical biological growth curve type curve and whatnot. And what it really covers, though, what it masks is a lot of things that took place beneath the surface. So, for example, if we put this in terms of aircraft technology in this time period, you're going basically from the very earliest monoplanes in the pre-World War I era through the first practical propeller-driven transports of the early 1930s, through the first practical turbojet transports of the 1950s, and on up to vehicles that are getting fairly exotic, you know, sustained Mach 3 cruise with the Lockheed Blackbird, things like that. Now, if you break down that curve and you take a look at it in a more detailed fashion, according to aircraft type, you see actually you're dealing with a bunch of curves, okay? You have piston aircraft typified by high-speed aircraft such as fighter airplanes, and you see that that curve breaks off at about the 0.7 Mach number, 0.65, 0.7 Mach number in the mid-1940s. Piston airliners continue on out into the early 1950s, and they're basically at about the Mach 0.45, Mach 0.5 region. Then you see the tremendous advances that we saw with turbojet propulsion, and then the rocket research airplanes. And once again, this is taking a look really at only going through like that Mach 3 regime when you're taking a look from the middle 1950s perspective. And you see a funny thing take place, and that is in the middle 1950s, you start to see what really is a plateau. You know, jet fighters peak out at about Mach 2. They're still really in that region today. Turbojet airliners in the 0.82, 0.84, 85 region, things like that. And so there's this plateau, but is there really a plateau here? Well, actually, if you take a look at it, there's many, many different things taking place in that plateau if we run this out to the present day. Composite structures, more efficient propulsion systems, the advent of the turbofan, thrust to weight ratios because of engine technology going beyond 1, digital fly-by-wire, low observables for military airplanes, the so-called stealth revolution, refined transonic aerodynamics with Dick Whitcomb and the supercritical wing, satellite-based navigation, unmanned aerial vehicles, sensors, command, control, communications, computers, intelligence, surveillance, reconnaissance, C4ISR as we term it. All these things are feeding. And then we have this big question mark that we've been dealing with over about the last 5, 6 years, and that's what's next. Well, what's next is everything you're reading about today, you know, drones, urban mobility, hypersonic, stuff like that. And we'll get to that part in a little bit. But just to do some review, the 20th century was really a century where we had a 3-dimensional revolution. We were able to operate above the surface of the earth. We were able to operate under the surface of the sea. And so mobility really became 3-dimensional, if you will, with the advent of the airplane, the submarine. And the airplane side of the story began in 1903, of course, at the end of the year when the Wright brothers flew at Kitty Hawk. And this aircraft here, which is in some respects almost like a powered kite. Now, surprisingly, although we invented the airplane in the United States, by 1912, for a whole series of factors, we really started falling behind. And the country that leapt to the forefront of aviation technology in the immediate pre-World War I time period was France. And I use a slide here showing 2 comparative aircraft from 1912 perspective, one a Wright airplane, one a French airplane called the Depetazan monocoque racer. Monocoque means shell, as in that shell design of the fuselage, streamlined fuselage shape here made out of wood. And you can see the Depetazan is about, you know, it's not quite twice as fast as the Wright so-called Speed Scout, but it's certainly getting up there in terms of miles per hour. Now, by the end of the First World War, the leadership in aviation technology had actually passed to Germany, we've just passed the 100th anniversary of this particular airplane. This was an all-metal, low-wing cantilever monoplane called the Junkers F-13, and it basically sparked a whole air transport revolution a century ago. And this kind of approach, the low-wing, all-metal or all wood, wood and metal combined type structure, really started to influence aircraft design in that time period. Here's an early racing aircraft from the 1920s, kind of a chesty looking little vehicle here, but actually quite refined in its own way. And the problem with this technology is that basically we're dealing with insufficiency in terms of aeronautical propulsion. We simply don't have the refined aerodynamics to make very highly streamlined, highly efficient airplanes on one hand. And on the other hand, the engines we have are relatively low powered engines. And a good example is the 1920s is the time period in which we see a lot of investment in what we call trimotors, three-motor airplanes. And the reason you have that is because the drag loading of the aircraft was so great that if you lost an engine and it was a twin engine airplane, it would descend and crash. You know, it's that old joke about twin engine airplanes, the second engine takes you to the scene of the crash. Well, the trimotor airplane at least guaranteed that you could somewhat remain aloft if you lost one of the engines. And of course, that's a commentary on engine reliability at that time. So there was a great deal of work done in the 1920s on refining propulsion. We came up with controllable pitch propellers, such as you see here. We came up with refined cowlings that not only streamlined the flow of air through the and around the engine, but also streamlined the flow of air around the aircraft itself so that you've got benefits both in cooling and both in reduced drag. And so what we had then in the 1930s is we had a genuine aircraft revolution where you had advanced all-metal structural design coupled with refined aircraft design, streamlining primarily the low-wing monoplane, internally braced wings and tail surfaces, retractable landing gear, engine cowlings, controllable pitch propellers. And that sets the stage then for what becomes a genuine design revolution. So that by the late 1930s, it's a revolution that we in this country are really leading, thanks largely to one major manufacturer, the Douglas Company, now part of the Boeing enterprise. And what this really gives us is it gives us a dual use industrial base. It's one that you can apply to civil aviation. It's one you can also apply to military aviation. And this is really thanks to one big thing, and that is the maturation of the piston engine. The piston engine, which by this time is giving you about 1 horsepower for every pound of engine weight. So 2,000 horsepower engine weighs about a ton, okay? But what people don't really appreciate, certainly not in the engine community, is there's a revolution about to come. And that revolution is a revolution that's going to be a revolution involving high-speed flight, and it's going to require dramatically different propulsion. And the revolution, the first indications of it, oddly enough, come about in 1919. And that's when, if you take a look at the aerodynamics of propellers, and of course a propeller is nothing more than a rotating wing. If you take a look at the tip speeds of the propeller are approaching the speed of sound. In some cases, they're reaching it. And what you're seeing is a dramatic increase in drag and a dramatic decrease in lift. And so you're having all the classic problems that an airplane with a wing will have if that airplane approaches the speed of sound at the same time. Now, we were starting to see one form of propulsion that would play an influential role in high-speed flight. And that was the advent of the rocket engine. The rocket engine, of course, goes back to antiquity. The black powder rocket goes back to ancient China. But this was the development of the liquid fuel engine. And then later on, the development of solid fuel engines that had much more complex solid fuel oxidizes and mixes. The Kitty Hawk of rocketry began in 1926, March 16, 1926, when Robert Goddard, shown here on the left in this slide, fired this really weird looking little rocket which is called a repulsor. The rocket is actually at the top of the slide. And it flew for about a second and a half, not very long, but it did prove the practicality of the liquid fuel rocket propulsion system. Now, by the mid-1940s, the Germans were developing long-range, what we would call theater-ranging ballistic missiles today as terror weapons, the so-called V2 missile. And this coincided with the advent of a crisis in conventional aeronautics, conventional aerodynamics, what was referred to at the time as the compressibility crisis. And what it basically was, and this is from a working paper by a very distinguished engineer named John Stack. He was a major figure within NASA, and before NASA, the National Advisory Committee for Aeronautics, its predecessor. And Stack was very concerned what happened when you put a model in a wind tunnel. When you put a model in a wind tunnel and you blasted the air around it and you reached very high transonic speeds where you were getting to a flow in the tunnel of about Mach 0.75, 75% of the speed of sound, moving towards Mach 1, the tunnel would start to choke. And this was because you were getting flow interference off the model. You were getting the formation of local shock waves from accelerated flow around the struts holding the model and around the model itself. You were getting reflections of these shocks around the tunnel. And as a result, your reliability in the tunnel and your ability to really use that tunnel for meaningful research between, say, Mach 0.75 and then Mach 1.25 on the other side, that 0.5 Mach number region in there was basically a big question mark. Oddly enough, if you got completely supersonic flow through the tunnel, and of course you had then streamlined flow lines off the model, the reflection problem went away. So once again, you could get very good high-speed tunnel data. You could get very good low-speed tunnel data, but it was like the three little bears in the porridge. You didn't get that just right mix in the middle. So he proposed, instead of using wind tunnels, he proposed that maybe we actually needed to develop specialized streamlined aircraft that would be instrumented, that could be used to fly within the high-speed regime, which he defined as roughly 450 miles an hour and above, to get basic data. Now, this didn't really go anywhere at the time, but it was in many ways the birth of what we would call the research airplane concept, which became very, very important later. A more interesting development that took place at the time was that of a German fluid dynamicist named Adolf Busemann, who in 1935, at the Volta Conference in Rome, promulgated the swept wing as a means of alleviating transonic drag rise and in effect fooling the air into thinking that the wing was going slower than it actually was. Now, this paper did not gain a great deal of attention at the time, and I've often wondered why. And I think it may be because of this drawing that you see in the upper left here. If you take a look at his swept planform, that's a very slight angle, sweep angle that he shows. It's not that different than what people are seeing on conventional transport airplanes of the time. Think of the DC-3, for example. If you fill in the trailing edge, it has a swept leading edge that's somewhat like that. And so I don't think people necessarily in their own mind thought of this as revolutionary as it truly was. But Busemann certainly did. And by 1940, the Germans, who were pursuing the development of rocketry to offset some treaty limits that had been placed upon them after the First World War, the Germans were exploring the idea of very long-range rockets that might actually be lifting reentry vehicles using sharply swept, what we would call low aspect ratio wings. So here's on the left side, you see a 1940 Schlerin photograph of a wind tunnel test taken at Peenemünde of a A4, which was the technical designation for what was known as the V2 operational weapon. And on the right-hand side, you see the so-called A4B, which was an experimental variant of the V2 with a low aspect ratio wing that was flown in 1945. We'll mention this a little bit later. Now, while people were looking at the very high speed side of things here, there was a practicality that was actually quite risky. We were developing in the 1930s around the world, all the world's leading aeronautical nations were developing high-speed fighters. You know, we kind of think this is a little bit ludicrous because today they don't even have a top speed that's even half that of, say, a commercial business jet. But at the time, these were considered high-speed airplanes. They typically had a radial engine or a inline engine, streamlined engine in the nose, but the configurations of them were relatively awkward, lots of bumps and humps. Yet, in a high-speed dive, they could reach about 0.7, 0.75 Mach number. And when they did, they would start to encounter high drag rise, a shift in the center of lift, the development of turbulence, turbulence that would then beat the horizontal tail of the airplane to death, so to speak. And on the more streamlined airplanes that could get to higher Mach numbers in a dive, say 0.76, 0.77, this actually became quite dangerous because if a pilot tried to pull out too quickly, he could exceed the structural load limits of the airplane. And the first example of this took place in 1937 when a German test pilot named Jodelbauer was killed flying an early Messerschmitt 109. We were not immune in the United States. We had tremendous problems with this airplane, the P-38, which in 1941, during a highly publicized dive test during contracted testing in California, the tail came off the airplane. So the predecessor of NASA today, the National Advisory Committee for Aeronautics, which lasted from 1915 to 1958, undertook a whole series of dive tests using instrumented airplanes. This is one of them here, a Navy fighter called the Buffalo. Not a very good airplane, but it was used as an instrumented aircraft to engage in high-speed dive tests to try to get some understanding of flow conditions around an airplane. When, during the Second World War, we were developing higher performance fighters, we used some of these for dive testing. And so here, for example, is the P-51, later known as the Mustang. In the early days, it was known as the Apache. And you see this airspeed boom here. And notice that the gun ports here are sealed over. You don't see any gun ports here. And that's because the guns have been removed. And instead, you have an instrumentation package put into the wing together with all sorts of pressure taps and whatnot to study what's actually happening to this airplane. And what is happening to this airplane? Well, if you take a look at what's happening to this airplane, and this is from NACA Technical Note 1190 by a guy named D. Beeler in 1944, you notice that when you get to about Mach 0.7, all of a sudden you see this abrupt drag rise, okay? Where the drag seems to be going asymptotic, okay? This is 0.8. 0.9's out here, speed of sound is out in this area. You can't even get there from here. I mean, the drag on this thing is just going sky high, okay? Now, this is not a distorted tunnel test where you're getting mixed flow and uncertainty. This is actually real-world dynamic testing of an aircraft in a high-speed dive. Now, if it's in a high-speed dive, it's diving from higher altitude to lower altitude. Therefore, it's diving from thinner atmosphere into thicker atmosphere. Therefore, it's getting itself in a world of hurt as it gets into that high dynamic pressure environment as it's operating in the lower atmosphere, okay? Now, there were various stopgap methodologies people tried to play with. You know, this is another view of a later model Mustang, a more advanced Mustang called the P-51D. And you'll notice, once again, there's that ammo bay for the machine guns. The machine guns are out, the ammo's out. Instead, what you have is in here, once again, is instrumentation. But in this particular case, it's connected to a model. And this model is actually on a pivoted point here so that you can use the accelerated flow over the wing, very close to the wing surface, to get high-speed flight data. The airplane itself may be diving at about 0.7, 0.75 Mach number, but the accelerated flow over that wing may be supersonic at that point. It may be already Mach 1, in which case you're getting a standing shock wave, you're getting turbulence behind the shock, beating the horizontal tail over here to death, that sort of thing, okay? So this is an example of a stopgap methodology. Another was simply to take a high performance bomber like a B-29, fly it above 30,000 feet, and then drop a weighted shape out of it. A shape that you had already studied in the tunnel or whatnot, so that you understood the basic characteristics of it, and then you could do radar tracking of it. You might even have some instruments in it, and you could try to get some measurement of drag and some understanding of what's happening to that shape as it's falling from the upper atmosphere. There were even model tests shown here where people actually dropped models of aircraft configurations that were being experimented with. In this case, the first supersonic airplane, the Bell XS-1. Another stopgap methodology was the rocket-propelled model. In this particular case, you simply take a model, you fire it off, and this method, we still use this in some respects today even. You fire it off, and then you measure what's happening to that model as it's flying out over the Atlantic. The launches were made out of what is now the NASA Wallops Launch Center. Now, of course, you have scaling issues when you're dealing with models as opposed to full-size vehicles, but nevertheless, you can get some pretty good information on things going on. All this is designed to basically overcome one problem, and that was the problem of transonic testing in wind tunnels at the time. And that problem was not resolved until the end of the 1940s, when we had the advent of the so-called slotted throat wind tunnel. Now, what that led to was it led to the development of specialized research airplanes. And the specialized research airplanes came about at an interesting time, because we had had, at the end of the 1930s and into the 1940s, the advent of a radical new form of propulsion, and that was the gas turbine engine. It was a revolution that began in Germany and Britain, and then was transposed over here to the United States. There were two major figures. One was a British guy named Frank Whittle, who first conceived the jet engine, the gas turbine engine, and then a German named Hans von Ohain. And they were both fortunate enough to get a mix of industrial and governmental support that they were able to go ahead. Aware of their work in 1941. Actually, we became aware of Whittle's work in 1941, and the government arranged for the importation of Whittle engine technology. And we made a research airplane using General Electric jet engines that copied this Whittle engine technology. So we got into the jet engine business in 1942. By 1944, you were seeing the first operational jet fighters. Now, the jet engine gave you the promise of flight above 500 miles an hour. But now, if you're going to operate in level flight at 500 miles an hour, you're right in the middle of the sweet spot for all these problems with compressibility and stuff like this. So now you have to resolve those high-speed flight problems. Well, at first we take some of these early jets and we instrument them and we use them for dive tests and stuff like that. And people realize, you know, this really isn't the safest thing you've got going. The British started an experimental research program that was actually quite ambitious in 1943. It was for an aircraft called the Miles M52. This would have been a highly streamlined turbojet airplane. The pilot would have sat in the inlet. Not sure most pilots would be very happy with that, to be quite honest about it. But this thing was going to be turbojet powered with an afterburner on the back end, which itself was kind of a novelty. It was canceled in the spring of 1946, which was a huge, huge mistake. Nevertheless, if we take a look at this vehicle, we see some of the hallmarks that we would see today of high-speed design. Now, what you'd want is you'd want to have an area-ruled fuselage here where it's pinched in. You'd want to have that horizontal tail lower or maybe angled down like an F4 or something like that. But the wing thickness, the tail thickness, I mean, all that stuff works pretty well. Now, any idea that the swept wing was going to be a panacea for high-speed flight kind of went out the window in 1946, when we had an accident in Britain to this particular aircraft called the de Havilland Swallow. It was a tailless aircraft. Now, I mentioned earlier that when you got into the transonic region, you would see pressure changes on the wing. And so with a transonic tailless aircraft, this is in the pre-fly-by-wire computer era, because in the computer era, you could control this. Like the B-2, you can control it, and it has these kinds of issues. But in the pre-fly-by-wire era, you would get longitudinal pitching motions, oscillatory motions, and they would either be, steady state in periodicity and amplitude, or else you would have, worst case, you'd have divergences. You'd have a increase in amplitude and you would have an increase in frequency, and both happened to the de Havilland Swallow, which shed its wings at Mach 0.87 at low altitude, did a violent pitch up, and the pilot was killed. That indicated that the sound barrier had teeth. Now, by this time, as a result of a meeting that had taken place in 1943, when you had the head of the Royal Aeronautical Establishment come to Washington, we had launched in America what we now call is the X-Series program. The X-Series aircraft that you still hear about. The origins are back in 1943, December 1943, followed up then with a meeting in March 1944 that basically said, okay, this was at the old Langley Research Center, now NASA Langley Research Center today. In those days, it was called the Langley Memorial Aeronautical Laboratory. And the idea was, okay, we're going to have two approaches here. On one hand, we're going to have an approach by the Navy working in conjunction with the NACA. They're going to develop a kind of traditional aircraft. It's going to have a jet engine. It's going to have a highly refined, almost like a test tube-like body on this aircraft. And it's going to be a high-speed aircraft that will cruise around just below the speed of sound and accumulate a tremendous amount of data. The Air Force, on the other hand, said, actually, we want to go faster. We want a rocket engine. We want this thing to fly through the speed of sound. People said, you can't really do that. And they said, well, okay, we'll call it the Mach 0.999 airplane. That was kind of like a joke, you know, referring to the so-called impenetrable sound barrier. And the guy who came up with this was a man named Ezra Kocha, who was an academic who at that time was working with the Air Technical Service Command at Wright-Patterson Air Force Base, Ohio. Out of this came an airplane, very famous. You can see it, the original of it, up at the Smithsonian at the Air and Space Museum, the so-called Bell X-1. It had two wings. The X-1 number one had a wing that had an 8% thickness chord ratio. The number two airplane had a slightly thicker 10% thickness chord ratio. Now, both those thickness chord ratios were well below the thickness chord ratio of conventional fighters in those days, which were anywhere between, say, 15 to 18% thickness chord ratio. Because we were uncertain the load limits that the aircraft would have to withstand, it had an 18G, positive 18G load limit. I'm not sure, you know, what you do with the pilot after 18G, but the airplane at least would survive. We knew so little about supersonic design that the fuselage shape was based on that of a 50 caliber bullet, simply because ballistics tests indicated that the 50 caliber bullet had a stable deceleration characteristic as it came back through the speed of sound. It had a horizontal tail. We realized that the closer you got to high-speed flight, very often you got changes in longitudinal pitch effectiveness. And so the horizontal tail was adjustable. You had on the trailing edge of that horizontal stabilizer, you had a conventional elevator to control pitch, nose up, nose down. But also the horizontal stabilizer itself was pivoted so that if you needed to, you could use a stabilizer trim switch and you could increase the tail volume to get increased longitudinal control authority for either pitch up or pitch down. It would have an instrument package of 500 pounds right on top of the center of the fuselage here. And it was intended at this time for ground takeoff, which in retrospect was not so, because you wouldn't, you know, here was a high performance 6,000 pound thrust rocket engine aircraft with conventional landing gear, heavily loaded, and you were going to operate this thing off a runway. You know, if the engine burst, you were probably going to lose the airplane. Cooler heads prevailed, and eventually they modified it for air launch, which made perfect sense. Here's basically what it looked like inside. Originally, the original X-1 was supposed to have conformal tanks that were just like basically modified cylinders. And the fuel was to be sucked out, fuel and oxidizer were to be sucked out by a turbo pump and expelled then into the engine, a 4-barrel engine, which each of the 4 thrust chambers producing 1,500 pounds thrust. But the turbo pump fell behind schedule. And so Bell instead put in two spheres. The alcohol water tank is a semi-sphere. And then they stuck in a whole bunch of little high pressure bottles and manifolds to give you a blowdown system that would basically expel the propellants into the tank. Well, what that did is it cut down on the useful volume of the fuel. So the airplane's powered flight endurance went from 4.5 minutes to 2.5 minutes, which meant that now you really had no choice but to air launch this guy in flight. Now, the engine itself was very, very simple. It was not throttleable. You simply fired a permission switch, 1, 2, 3, 4 little switches in 1,500-pound thrust increments, and that gave you the full 6,000 pounds of thrust, okay? Here's the instruments, there's the instrument bay. Of course, the airplane was wired with manometers, strain gauges. It could telemetry, it had early telemetry to telemeter data back. And it began flying in 1946. This is one of the early test flights of the second XS-1, so-called 46063. The first one, the first supersonic airplane, is 46062. And that's Edwards Air Force Base. That's the Atchison, Topeka, and Santa Fe Railroad down there by Highway 58. And that is beautiful country out there. I got to tell you, if you like flight tests and you like the desert, it's wonderful. I spent many years in Edwards, and you know, it's just fabulous. But anyway, think about that in your own career progression. Now, moving right along, here's the X1 test team. Now, this guy here is very famous. You've probably all heard of him. Chuck Yeager, first supersonic pilot. Walt Williams was the NACA engineer who basically ran the test effort out at Edwards. Dee Beeler was his chief engineer. I'm sorry, this is Dee Beeler here, chief engineer. Chuck Yeager's buddy, Jack Ridley, was the Air Force project engineer on the project. This is Gerald Trzynski here, who ran the instrumentation for the X1. Later set up the whole NASA spacecraft tracking network that we use to the present day. And this was Joe Venzel, who was the NACA's senior pilot. He was out of the cockpit at this point, and he had one great characteristic. I knew Joe Venzel before he died. Really neat guy. He was absolutely profoundly deaf from all his years in open cockpit airplanes. And very often in meetings, if he didn't like what was going on, he'd simply turn his hearing aid off and go to sleep. Great guy. But anyway, this is a historical item right now. If any of you have this, they're probably worth some money. That's a slide rule. To show you how old I am, I actually learned how to use a slide rule. This is before the days of hand calculators. You know, we had a chance in the 1970s to buy some hand calculators for an office I was in, and we absolutely freaked. We spent hundreds of dollars, bought these calculators and whatnot. And frankly, nowadays, if you open a bank account, you probably got a calculator as a free gift that has like 100 times the power, the computational power of these things that we blew a wad of bucks on in those days. Welcome to the future. Anyway, this is the most famous photo out of the early supersonic era. This is the Bell X1 on its actual supersonic flight. It has just gone through Mach 1. It is catching up with a chase aircraft flown by a guy named Bob Hoover. And Bob Hoover has a camera system, and it catches it as this thing goes screaming by. It's still doing about 0.9 Mach number at this point. Only one thrust chamber is firing at this point. And the critical data was 1.06 Mach number, 700 miles an hour, 43,000 feet in relatively level flight. And here's the data trace, which I thought you might like to see. And of course, between these points is the time period where the aircraft is actually going supersonic. Okay, so I mentioned the swept wing with Buseman. Oddly enough, we independently discovered the swept wing, an engineer named Robert Jones, at the end of 1944. And then when we discovered the investment that Germany had made in the swept wing in 1945, we decided we needed to do something with this. But the swept wing also gave you some problems at low speed. You had a lot of handling qualities problems and issues. So oddly enough, the first swept wing airplane that the United States makes is where we modify a Bell piston engine fighter with a 35-degree swept wing. And we play all sorts of games with the leading edge, with flat combinations, flap combinations, things like this, to try to get some information on whether we can actually apply this to high-speed aircraft. okay, so that they're safe in the low speed around the pattern regime. At the same time, the military services, having funded this Navy project called the D558 and this Air Force project called the X1, say, well, geez, you know, if swept wings look like the next big thing, we got to get in on this. And so the Navy says, well, you know, we were going to build 6 of this D558. Why don't we just build 3 of them? And we'll take the other 3 and we will design them as special purpose swept wing research airplanes. So the NACA said, well, if you take a D558 and you put a swept wing on it, it's going to look something like this. And there was an NACA engineer at that time, and his name was William Pearl. And William Pearl looked at that and said, yeah, thanks very much. I think we can do something with that. And William Pearl was a Soviet intelligence agent. And so he takes it to the Russians. And if you take a look at the MiG-19, that actually looks pretty much like a MiG-19. Thank you, William Pearl, who, by the way, then did a couple of years in jail when we discovered that he was, you know, basically a traitor. Anyway, Douglas came up with a special purpose design for what they called the D5582. And the aircraft initially appeared with a flush canopy, but the visibility was so bad, they modified it to have a step canopy. It had mixed propulsion, both a jet engine in the belly of the aircraft and a rocket in the back. But then Douglas got smart, the Navy got smart, and they said, look, we don't want to operate this thing off the ground. It's like the Air Force with the X-1, too dangerous. We'll launch this thing in flight. And so they modify it to all rocket propulsion. And this aircraft in 1953, flown by a pilot named Scott Crossfield, becomes the first Mach 2 airplane in history. It just gets just across the line, 2.005, fully instrumented flight, so we know that's a real number, during a slight dive at 62,000 feet. And that aircraft itself is now in the Smithsonian. We apply the swept wing very quickly. In typical leader-follower fashion, you go from research aircraft to operational military airplanes, typically fighters and bombers. And then from that, down into the commercial world. And that really kind of sets us up for the stage of what we have today, post-war air supremacy, you know, all sorts of aircraft for reaching around the world, transportation, power projection, naval superiority, some interesting technical developments, Mach 3 sustained cruise, hypersonic flight, which we'll get into, low observables, stuff like this. This is sort of like where all this begins. So if we take a look at this high-speed expansion, beyond having gone now through the speed of sound, through Mach 1 in 1947, Mach 2 in 1953, we find that there's a very rapid acceleration then that takes us to Mach 27 by 1965. And this really takes us right into the midst of the hypersonic regime. And so we're turning now really into the advent of hypersonic flight. Hypersonics is now the stuff of newspaper headlines, stories. Where are we going with it? People lose sight of the fact that we've actually had hypersonics underway for over 70 years. And we've actually had operational hypersonic military systems since the late 1950s. When you got into the ballistic missile and you had the reentry vehicle that typically carried a warhead, or where you were recovering a returning spacecraft, be it a spacecraft that was used for sampling purposes or photographic reconnaissance, or where you might be returning a crew from space, things like this. That's practical hypersonics. So it's been with us for a very long time. And basically, if we take a look at hypersonics, we can take the classic missile and space programs that we think of, you know, Atlas, Mercury, Gemini, Apollo, the great 3 inhabited spacecraft efforts prior to shuttle. We can take some of the classic high-speed projects that I mentioned, you know, the X1, the D558, some of their successes. And you see that there's basically this confluence of the two. And, you know, these have given us a number of projects, not all of which have flown, but some of which have flown and been quite outstanding. For example, the X-51 that I mentioned here at the end. So this is actually kind of a significant thing. What we have accomplished over this time period is we've basically done three things. We've refined design approaches. We've mapped the whole frontier all the way up to orbital velocity and back down. And we have achieved some notable milestones engaged in what we might say true transatmospheric operations, where you pop out of the atmosphere, you pop back in, you do something. We're going to go even further than this. You know, if you take a look at what we see now with this idea of space tourism, or the experiential space flight, where somebody like, say, Virgin Galactic or something like this, somebody launches in a spacecraft up to Mach 3.5 or 4 just to pop out of the atmosphere. That all sounds just like fun. But if you take a look at it, that's giving us the ability to do research, practical, reusable space exploitation of the transatmosphere and above. And it's very, very intriguing to see where this is probably going to go. It's like barnstorming in the 1920s, which anticipated the development of commercial aviation. Now, hypersonics, as we know it, really begins with this beast here. This started out in the 1930s as a study project by two engineers, a Austrian engineer named Eugen Zenger, and his mathematician wife, Irina Brett. And it was the so-called Zenger-Brett Silverbird, okay? It was intended to be a space support vehicle to support either an inhabited space station or to insert satellites in orbit, things like this. Now, when World War II came along, they wanted to get continued funding to keep their study effort going. So they decided the way to get continued funding for this was to try to transform it into some sort of form as a military aircraft. And so they said this could be a long-range bomber, a so-called Fern bomber. Well, it was ridiculous. I mean, the concept here was technically completely impractical, certainly from what Germany needed in World War II. But this was basically kind of a funding scam to get money. And finally, in 1944, the German Air Ministry said, look, we're not going to fund this thing any further. This thing is far removed from anything we need. And so they just wrote up a final report. But the final report was very, very influential because they did very hardcore studies on the requirements of high-speed flight. If you take a look at this configuration, this is actually a pretty acceptable configuration for high-speed flight. You have a flat bottom ogival body. You have wings with a supersonic cross-section on them, wedge airfoils. You have a 100-ton thrust rocket propulsion system. The vehicle is sled launched. You know, there's aspects of this that might not necessarily work real well. You might actually want to have like a delta wing vehicle here or something. But by and large, this is actually a pretty realistic conception for its time. So in the late 1940s, we started to see a transfer in hypersonic design technology from Europe to America. Just like we had seen that transfer of all metal aircraft technology, cantilever design, et cetera, after World War I to the United States, we saw the same thing here in the 1940s. There was a Chinese engineer named Xian, who was the chief technical assistant of Theodor von Karman, an emigre Hungarian scientist who ran the Guggenheim Aeronautical Laboratory at the California Institute of Technology. And Xian took a look at basically a German missile project called the Wasserfall, the waterfall. And he thought, you know, instead of launching this thing vertically, if we took off one of the fins and we operated as a long-range hypersonic test bed, we might actually be able to develop a transcontinental hypersonic boost glider. He forecast a hypersonic lift-to-drag ratio of around 4. That's a little bit high. You know, he was a little bit optimistic on this. Gross liftoff weight around 96,000 pounds. Everybody tends to underestimate their weights when they deal with early hypersonic vehicles. You know, they always think these things are going to be lighter than they would actually be. But this started people thinking about the requirements for what might be a possible hypersonic vehicle. And the first real attempt to do this was by a NASA engineer named John Becker, who, by the way, is still with us. John Becker lives up in Virginia. He's over 100 years old, mentally still very sharp, physically frail. And the result of this was a program begun in the 1954 time period for what was called round two. Round two was an allusion to the first supersonic research airplanes, which as a group were referred to as round one. Round two was to take us to Mach 6, 6 times the speed of sound. And the way Becker envisioned doing it was basically developing a winged rocket propulsion system where you would have a 50,000 pound thrust, 57,000 pound thrust rocket engine in the back end developed by a company called Reaction Motors, later Thiokol. It would be fed by a turbo pump, and the propulsion would be liquid oxygen plus anhydrous ammonia. You don't often hear much of anhydrous ammonia. It's not used that much in rocketry, but of course it's very energetic. It's the weapon of choice for terrorists, for example, because it is simply so energetic. You know, that's why a fertilizer bomb is so powerful. And basically, the interesting thing about this is because this would be an airplane launched from a launch aircraft, and they decided ultimately to use a B-52 bomber to launch it, it would have to have a mix of flight controls. You'd have to have conventional aerodynamic controls to fly it within the atmosphere. But then when you were in the upper atmosphere, in regions of very low dynamic pressure, you know, remember your engineering dynamic pressure Q equals 1/2 rho V square, you know, well, you know, you take a look at the upper atmosphere, you can have a pretty high V, but you know, you're in such a situation there that you still don't have enough air, so to speak, to grab onto. And so to maintain vehicle attitude so that you just wouldn't do some sort of ballistic tumble, you had reaction control thrusters, so-called cold rockets, hydrogen peroxide rockets in the nose to control pitch and in the wingtips to control roll, okay? And you also had these same attitude rockets in the nose to control yaw, nose left, nose right. The pilot was basically sitting in a completely pressurized cabin, and he himself was wearing a full pressure suit. So this is basically, if you will, a spacesuit type environment. Here's Neil Armstrong wearing the Clark MC2 pressure suit, which is really the forerunner of all modern spacesuits. And because you couldn't fly this vehicle often enough to maintain flight proficiency, it was the first research airplane that really required a sophisticated simulation system to maintain proficiency. And then, of course, researchers discovered if the system has that degree of fidelity, you can also use it for mission planning. And so that's where you start to see some very interesting interplays, is where you start to use simulation for mission planning. The study that Becker came up with for the X-15, this was his initial study for what the aircraft would have looked like. And you can see that the ultimate X-15, which we had here, really didn't look that different. There's differences in the tail configuration, but basically it's this same kind of vehicle. Now, the ultimate X-15 that flew was the so-called X-15A2. It had 2 huge external fuel tanks to increase engine burn time. It flew with a dummy supersonic combustion ramjet, although I stress this was a dummy. This was a boilerplate. It had no hot flow through it or anything like that. It was just basically a shape. And a guy named Pete Knight, William J. Knight, took this to Mach 6.70, 4,520 miles per hour on October 1967, a record for a piloted hypersonic vehicle within the atmosphere that still lasts. Now, if you looked at what people were trying to accomplish at this time in terms of the overall development of flight, the idea was that we would fly eventually in these sophisticated winged vehicles out into space, and we'd be able to basically then return like a winged vehicle through the atmosphere. But there was a shortcut that came along that people didn't really think about. And that shortcut was blunt body reentry theory. The development of the ballistic missile required that we find some way to protect a returning warhead shape so that it could actually get through the atmosphere. And H. Julian Allen and Alfred Eggers, 2 engineers at what is now the NASA Ames Research Center, did some studies on reentry shapes and concluded that if you had a blunt nose, if you had a rounded nose, rather than a pointy nose, that actually you would develop a detached shock wave that would stand off from that nose, and it could carry off about 90% of the heat load of reentry from that nose, which meant that now you could design the nose to have like ablative cooling or maybe radiative cooling. It didn't have to be very, very heavy or whatnot itself, because you're carrying off most of that heat simply because you're forming this detached shock wave around the nose. To put this in practical terms, here's your nice pointy science fiction rocket with an attached shock wave right on that nose. And of course, the faster this goes, the hotter that gets, and eventually you're melting it down. If you then take a look at early blunt body theory, you see that what you get is you get a very strong detached shock. You can have, of course, a lot of turbulent wake flow behind the vehicle. You can tailor the design of that shape to reduce the wake flow, and you can still get a pretty strong shock here that slows you down and carries off a lot of heat. And then eventually, if you take a look at this, we're at the point where we're able to develop either missile warhead shapes, or we're able to develop manned shapes like the Mercury vehicle, so that we're very quickly able to apply this to lifting reentry spacecraft, to ballistic vehicles as they're coming through the atmosphere. There was still a great deal of interest, however, in finding a way to use advanced aerodynamic tailoring, design shaping, to get a hypersonic vehicle that could operate at the very upper levels of the atmosphere, or maybe pop out of the atmosphere into space and then return. And there was a debate that grew out of this. And the debate was, what do we need to do? Do we need to have the wing above the fuselage? Do we need to have the wing below the fuselage? Basically, if you had the wing above the fuselage, you got very good range, but you also had a very high weight, and you had a very high heat loading and very high, because that high structural weight, you had a lot of complexity. So there was a great flip. And the great flip basically meant that for most hypersonic vehicle design concepts, we use the same approach, but with a flat bottom, lower wing, and then a wing attached to the bottom of the fuselage, and then with end plate vertical fins. And the classic program here that exploited this was a vehicle called Dinosaur. Now, I have to tell you, as engineers, you're going to do great things, and you're going to have some really bright ideas. But be very careful the names that you pick for a project, because when you walk into a politician and you need money and you say, we want $450 million to build a dinosaur, that doesn't go over real well, okay? The name made sense. It stood for dynamic soaring, but in the minds of most people, when you mention dinosaur, it meant big, clumsy, obsolete, and headed for extinction, okay? So Dinosaur didn't get very far, which is unfortunate because it was actually a very advanced vehicle concept. It was canceled in 1963 when it was about 2.5 years away from first flight. And it was a vehicle, in retrospect, that we actually should have pursued. At the same time that Dinosaur was taking place, we had a lot of interest in getting away from dependency on the rocket boosted, the rocket lofted vehicle where you had basically a boost glider. And the idea was, well, maybe we can use some sort of air breathing propulsion system. Maybe we can use a ramjet to accelerate a vehicle so that it can actually fly into space. Now, you can't do this with a subsonic combustion ramjet, your conventional ramjet, where you take air in, it's moving subsonically through the flow path through the engine, mixed with fuel, expelled, etc. But if you have a supersonic combustion ramjet, in theory, you can actually take that vehicle all the way to orbital velocity. Now, I say in theory because actually, in practical terms, in all likelihood, you really do need a kick stage to get that beyond, say, the Mach 18, Mach 15, Mach 18 region. But two engineers, Weber and McKay, in an NACA paper in 1958, promulgated this idea of what we now term the scramjet, the supersonic combustion ramjet. Their work was supported by industry by a man named Antonio Ferri, who was plugged into the Republic Company, a leading figure in high-speed flight in his own right. And so we started to see these really exotic shapes that people were thinking of developing: Mach 7 global ranging hypersonic cruisers, a vehicle called aerospace plane that would have extracted air, chilled it, mixed it with fuel, and then flown into space as a single stage to orbit type vehicle. The problem was, when people took a look at these vehicles in terms of the practicality of them, they were huge. They were massively large vehicles, 1 million pounds gross liftoff weight, things like this. And they didn't really have any other practicality. At the time, we had a lot of issues we were dealing with where we needed to put investment elsewhere. And so those programs died. But there were some cheaper, lower cost efforts that were very, very influential and that had a major influence on the subsequent direction of hypersonic flight. One of these was this vehicle here called ASSET, the Aerothermodynamic Structural Systems Environmental Test. It's basically a very small Delta glide, a very small wings on it, obviously. You have a tilted nose ramp. This is the configuration it has when it's coming down from a flight out to about Mach 15. This is the angle of descent running through it here. So you have this vehicle that's operating a very high angle of attack as it's coming down. And you have this 10-degree tilted nose ramp. You have a 16-degree ramp back here for stability. A lot of blunt end flow around the back end, of course. Thick, rounded leading edges here emerging from the flanks of this truncated cone. And we learned a lot of things from this. One of the things we learned was the challenges of lee side heating, that the problem with heating wasn't simply on the bottom of the vehicle or on the nose, but that you got a lot of flow, vortical flow coming around the sides of that vehicle. So your lee side heating requirements were very, very demanding. Another vehicle that was built on the cheap was this one called PRIME, Precision Recovery, Including Maneuvering Entry. This vehicle is about 5 feet in length at the most, 4.5 to 5 feet in length. It was launched on the top of an Atlas ballistic missile over the Pacific Test Range, and it had a body flap that would pop open. And while it was flying, the body flap would be slightly differential so that it would begin a steady state turn over about a 700-mile range until it was recovered in Kwajalein Lagoon. Now, we take a look at this, and by the standards of things we're doing today with reentry vehicles, this is pretty primitive stuff. But what it's pointing us to is a new class of vehicles, and that is tailored body shapes that give you some of the lifting properties of a winged vehicle, but they also have, in some respects, the aerothermodynamics of a reentry shape. And out of this come a class of vehicles called the lifting bodies. We're not quite certain at this time how well they'll fly at low speed. So NASA and the Air Force get together and jointly fund a program where they build a series of these strictly for low speed tests. The first one is a plywood glider that could fly up to about 200 miles an hour. Then you had two heavyweights that could take you out to about Mach 1, 1.2 Mach number. Then you had another one that the Air Force sponsored of a slightly different shape, the X-24. It eventually was gloved with a more exotic body shape over it. And this really pointed us in the direction now of what would become the space shuttle. There were thoughts at one point of going beyond the X-24A to a thing called the X-24B, which would have had X-15 type propulsion, the LR-99 engine. It didn't go anywhere. It was supposed to be called the National Hypersonic Flight Research Facility. And so when we actually did get into developing the space shuttle, we basically did this on the basis of just laboratory work. We didn't do it really on the basis of active flight test efforts that we were able to target or focus specifically looking at the shuttle. This shows, of course, the shuttle undergoing one of its early hypervelocity tests in a tunnel down at the Arnold Engineering Development Center. Now, what we saw here really was the combination of theory, concepts, and then the practical research, development, test, and evaluation, forming a technical base, a base of both theory and experience. And this then taking us into two major roads. One was space access, typified by the shuttle. Another was what we might call global reach. And this was the idea for these piloted hypersonic aircraft that would fly around the world, things like this. And there was tremendous crossfeed between the two. There was a third strain we could have put in here, but it wasn't really broken out at this point particularly. It's become more important since. And that was the idea of the hypersonic missile. And that, of course, is one that's gotten a great deal of attention more recently as we take a look at national security concerns. But if we take a look at one aspect of this, we take a look at the space access issue, we see some interesting things. First of all, if you take a look at your blunt body shape, like say your Apollo command module, you have very low lift to drag ratios with that, of course. If you take a look at your lifting bodies, those tailored body shapes I showed you earlier, okay, now you're getting into the level of the shuttle where you're getting, you're a little less well than the shuttle. The shuttle is up in this region in here. And then if you take a look at the very highly tailored shapes, well, now you can get up to a reasonable lift to drag ratio, which means that you have very good cross range performance. With something like the Mercury vehicle down around here, or a ballistic missile warhead, you're dealing with very little cross range. With an Apollo command module, you have a cross range of maybe 150, 200 miles, something like that. But when you start getting up, the higher you go in hypersonic lift to drag ratio, now that you can start seeing measurable differences in cross range. The shuttle is about here. It gives you about a 1,500 mile cross range. The shuttle was designed to basically put a reconnaissance satellite system into orbit. 65,000 pound payload bay. The sizing of the bay is to accommodate a reconnaissance satellite. And the reason it has that big fat delta wing on it was so that if you did a polar launch out of Vandenberg, which you would be doing if you were placing a reconnaissance satellite in orbit, you might not want to be overflying the Soviet Union on your orbit, so that you can actually launch this sucker, deploy the satellite before you reach Soviet space, so to speak, and then you can make a hard right turn back to land at Vandenberg Air Force Base. That's essentially why you had the big delta wing. Now, looking at early concepts for the shuttle, you had what were called TSTOs, two-stage to orbit. Okay, these were fully reusable vehicles where you would have a flyback booster, pilot, co-pilot here, and you would have a flyback orbiter, and you didn't throw anything away. But these were very, very complex, large vehicles. You know, if you take a look at these, and take a look at the engine complex here, you have 12 booster engines in this first stage. You know, people used to jokingly refer to these as clusters last stand for obvious reasons. As NASA started refining its approaches, looking at shuttle, they adopted a semi-expendable model. And the orbiter configuration that they developed that was most influential was what was called the 040C configuration. This had three main engines. It had your reaction control thrusters in the wingtips. Later, those were moved to pods on the side of the back end. And it had this basically large cargo bay here, conventional delta wing. If you squint, so to speak, and you look at this, you can really see what becomes the shuttle itself as developed and flown from orbit in 1981 with John Young and Robert Crippen. This is a photograph of it during its first return and descent to land. Now, if we take a look at the recap of the shuttle, it accomplished a lot, but unfortunately, there was a huge price. And the huge price was we lost 14 people in 2 shuttle accidents. We lost Challenger, we lost Columbia. Both those accidents were unforgivable. They were both preventable, to be quite honest about it. There was inadequate planning. There was very bad programmatic execution where we lost those people. That did not need to be done. I lost 3 good friends on the loss of Challenger rather, and I find it unforgivable to this era. The other accomplishments that it had, you know, if you took a look at our ability to put payload in space, to build the space station, to do all the rest of it, it's arguable whether that was a worthwhile investment. I think on the whole, we can justify that it was, but frankly, if you take a look at it, the cost was huge. This was supposed to be routine space access, you know, multiple flights a month by a shuttle fleet. Everything would be great. Well, it turned out that actually there was a tremendous refurbishment cost involved in working with the shuttle and orbiting it and then refurbishing the pad after launch. So that if you take a look at the missions, the total number of missions by the 5 shuttles, and then you divide that into the total program cost over 30 years, that's more than $1 billion a pop every time you launch the thing. Now, to put that in comparison, if you have a heavy lift launch vehicle, say the old Titan IV or the Titan III before that, you find that those heavy lift launch vehicles typically cost you about anywhere from $450 to $600 million, which is why Elon Musk is such a genius. You know, if you can cut that back by recovering your first stage, and you can use that first stage several times, and maybe even more than several times, well, then obviously you're cutting your costs way down. And, you know, frankly, since you're all in Virginia, you really should make an effort to get down to the Cape and see one of his launches, particularly when he recovers that sucker on the first stage. It is very, very, very impressive to see what this guy's doing. So anyway, that was the story basically on STS and the shuttle. In the post-shuttle world, we've actually done a lot. There's a very successful system out there that we can't talk about a whole lot because not a whole lot of it has been released. And that's this system here called the X-37. It's run by the so-called Air Force Rapid Capabilities Office. It was developed by the so-called RICO, the Rapid Capabilities Office, to undertake classified space missions of very long duration. We've had several of these built, and they have operated for over a year at a time before being recovered remotely and landing. And they've proved out some very basic things in terms of the practicality of hypersonics. So that's really kind of interesting. The dream that we've had in hypersonics, though, this idea of continuing to have a complex global ranging system or a transatmospheric system flying out in space and back has really, in some respects, almost been a distraction. And one of the examples of this was a program long before your time called NASP, the National Aerospace Plane, the so-called X-30, undertaken in the 1980s, 1986 time period. Development started earlier. There was some engine tests on scramjets in the 1985 time period called Copper Canyon that were very, very encouraging. And the idea was we'll have a 50,000-pound vehicle here, just a little speedy dot with 1 or 2 guys as the crew. It'll be powered by a scramjet. We'll be able to take off from the ground, fly into space, turn around, come back, and do this routinely. The guy behind us was a man named Tony DuPont, a great visionary. And he was working at General Applied Sciences Laboratory and in conjunction with Pratt & Whitney. Well, when people started looking at NASP, testing it was going to be anything but simple. You'd launch either from Edwards, and you know this would be like a Mach 15 continuous 2G turn type flight. You're all occupying the entire U.S. Or if you're launching from the Cape, you'd be operating in the corridor here with Eglin, and you'd be operating all the way out to Edwards and all the way back. So, I mean, this is pretty demanding if you think about it. Worse than that, when you started trying to bring the vehicle to closure, in other words, when you tried to gut this vehicle so that it's completely balanced and you are actually achieving what you're setting out to achieve, bring the design to closure, as we say. You couldn't get there from here. The vehicle grew in size to 450,000 pounds, from 50,000 pounds. And they still had at that point a 3,000 foot per second velocity decrement. They still couldn't get there without having some sort of kick stage. Now, here's where I think a mistake was made. I think, and I was actually access to this program at the time. I think a big mistake people made was they failed to recognize how much they had actually accomplished. They had made major breakthroughs in fuel, major breakthroughs in structures, major breakthroughs in thermal protection, major breakthroughs in scramjet design, including this ACES approach, liquid air extraction and then combustion. They had a vehicle that was completely practical for the Mach 12 to 15 region. And they should have settled for that. We should have used this as a very high-speed research vehicle and maybe even used it with a strong back where you could pickle off a vehicle in the upper atmosphere off the back of it as a two-stage vehicle. I think actually this was an opportunity that unfortunately was lost. Now, after that time period, we saw basically an alphabet soup of programs of people trying to capitalize on some of the work that we've had at hypersonic. So we've come up with all these particular names for things. Many of these have been startups and then have died away. There's been a lack of persistency, and there's been a lack of consistency in terms of our approach in hypersonics. And that's kind of hurt us in the present day. There have been some remarkable developments, and some of them have been on the cheap. A good example is Australia, the Center for Hypersonics, Alan Paul, and a team of people down in Queensland who in July 2002 achieved the first in-flight scramjet ignition. It wasn't sustained. They were just trying to demonstrate ignition using basically some cast-off elements and almost like a hobby shop approach to putting this thing together. They did it very, very cheaply. There's been some false starts where we had some programs that had a great deal of promise that were started with great fanfare and then fell apart for various reasons. One of these, the X-33, they underestimated the challenges of building a composite fuel tank, and the composite fuel tank simply structurally was not able to be built the way it was designed and configured. The X-38, which was to be a crew rescue vehicle, based on the old X-24, the SV5 that I showed you earlier. It went nowhere, although it should have. And perhaps most sadly of all, this vehicle here, the X-34, two of which were actually built, but never actually flown. They were flown as captive vehicles, but they were never actually hot flown in flight. They've since been used by Sierra Nevada for some of the work Sierra Nevada is doing in some of its lifting reentry work. This was a very sad story. This program definitely needed to be supported far more than it was. There's been some cautionary tales. One of the problems we have in flight testing is that it is expensive. And so there's a tendency for people to build small numbers of things. Well, if you build small numbers of things, you better make certain they work well, because if you lose one, for a reason unrelated to the purpose of the test, that can get you in serious trouble. We have had a word come in that I basically don't like. It's this word technology demonstrator. Technology demonstration is something you do in a high school science class, okay? It's to demonstrate a basic principle of something. There's a difference between that and hardcore research, development, test, and evaluation. In the test and exploration world, you're going out there and it invariably involves risk. You should be willing to accept loss if you're trying to further something, but you should not have a situation where you're losing things for ephemeral reasons. And I'll give you an example. The X-43, we built 3 of these vehicles. We flew 2 successfully. The first one crashed after launch because a fin came off the booster. This was the X-43 up here. It didn't even get a chance to fly. A fin came off the booster. That, by the way, is a traditional problem in missile testing and high-speed weapons separation, fins. And it's classic aerodynamic flutter and resonance issues. You know, if you're ever charged with building a fin, take whatever the calculations you have for loads, this is my personal advice, and double them, okay? Just double everything, because that's probably gonna work better for you. We had some concepts that were intriguing but were oversold. One of these was a vehicle called Black Swift, which was promoted as a global ranging hypersonic reconnaissance system. And basically what it was simply a takeoff from the ground, fly up to 60,000 feet, hit Mach 6, turn around and come back and land. And when people realized that it was being oversold, support for it dropped. You know, there's an integrity issue here. If you're going to propose a program, be sure you're proposing what actually the program is. We had a program called High Fly that the Navy had. Very interesting program. This shows it being dropped off in F-15 testbed aircraft. The problem was there were 2 launch attempts, and in both cases, the launches failed because of silly reasons. In one case, the missile fell off the pylon. In another case, there was a wiring problem and a short occurred and the missile fell off. You know, that's ridiculous. And the program wasn't proceeded with because of that. We had a program called HTV-2, which was run by Lockheed Martin. The first one failed after separation at very high Mach numbers in the vicinity of about Mach 15 or so. There was some useful data gotten back from that, but the second one then was flown without any changes in mission plan and under the exact same dynamic circumstances. And so the second one was lost too. And you think, you know, maybe there should have been a little bit of redesign done here, or maybe we should have looked at a different way to approach it. But we've also had some notable successes. One of these was a program called X-43, which, you know, I pointed how we lost the first one because of a fin. Well, the number 2 and number 3 aircraft flew successfully, the first to Mach 6.8, the second to 9.7. And we actually were able to get, this was a so-called hypersonic cruiser configuration. We were actually able to get sustained hypersonic combustion for just a few milliseconds through that engine. Now, the engine was burning itself up at the time. This was not a thermally balanced engine. It was not a practical approach, but it did give us first experience with a functioning, practical, accelerating scramjet. Beyond this, the one that was most successful was pushed very strongly by a very good friend of mine, a notable figure in hypersonics named Dr. Mark Lewis, former president, by the way, of the American Institute of Aeronautics and Astronautics, former chief scientist of the Air Force, and most recently a former Undersecretary of Defense. This basically took, once again, a hypersonic, what we call cruiser configuration. You see the forebody here, tungsten nose for basically weight and balance purposes. You have the scramjet inlet here. You have the scramjet module and nozzle area back here. Your fins for guidance and control. You have an interstage. The interstage has a vent in it so that when you fire this sucker up, you're not going to cause back end damage to the vehicle. And then you had a modified Army ballistic missile called an ATACMS booster attached on the back end. Total weight of this vehicle, if you took a look at the whole thing, it's about a 5,000, 5,500 pound system, okay? $240 million program for 4 vehicles. Here it is, in place, standard weapon pylon, mounted under a B-52. You know, if you follow hypersonic missile technology and applications for long-range power projection, this is basically what you'd be looking at if you were looking at a practical hypersonic weapon carried by something like an F-15 or a B-52 or a B-2 or the new B-21 or something in the future. There's the sort of rakish shape of it. Well, there were 4 flights. The first one got up to Mach 4.87, I should say. This was the so-called Kitty Hawk moment. You know, by that, What this was the moment that showed that you could actually get a thermally balanced hydrocarbon fueled scramjet burning conventional hydrocarbon fuel, not something exotic like liquid hydrogen or something like that, but something that you could actually see being used routinely in service. It used JP7, plain old JP7 fuel, the same fuel used in a Lockheed Blackbird. The second flight had a complex problem. It had so-called inlet unstart. The X-51 ignited, started to climb out, and then they had a blowout of a seal, and that caused the shock wave to pop out of the inlet. And so they weren't able to get a recovery on it, and it fell on into the Pacific. The third phase, once again, fin failure. The third flight, we lost the fin during boost. Unforgivable, very, very sad, okay? So now we had 3 lost. You got the fourth flight in May of 2013, and this was a very important one, 240 seconds of accelerated flight in a climb, the so-called Lindbergh moment. We got, just like Lindbergh flew across the Atlantic, the biggest accomplishment of Lindbergh's flight was twofold. He could stay awake for 33 and a half hours. That was number one. But number two, he was flying a single engine airplane, and it demonstrated the revolution that had taken place in propulsion technology with the radial piston engine at that time. Well, this is kind of like a Lindbergh moment. When you're flying 240 seconds, going basically a mile a second or a little more, that's telling you got an engine system here that works, and works very, very well. Indeed, in tests in a Langley 8-foot high temperature tunnel of the X-51's engine, the engine was tested multiple times. You could run it over and over and over again. It wasn't like the X-43 engine that was burning itself up even as it was functioning. So basically, those are the two big moments. As I said, the Kitty Hawk moment, the not a fluke flight of the Lindbergh moment in 2013. And I'd just like to basically leave us now, before I finish, with a thought. And that is, if we take a look at mobility and rates of mobility over time, you find that we entered the 19th century at the speed of about 6 miles an hour. It was the speed of an animal-drawn vehicle. This is just at the beginning of the Industrial Revolution, okay? And then very quickly, you had the development of the steam engine, so that by the end of the 19th century, as we entered the 20th century in 1900, you had strategic mobility of about 60 miles an hour, thanks to the steam locomotive. And then we had the development of the internal combustion engine and the development of the gas turbine, a very, very fine, I think, largely still unappreciated, so that we entered the 21st century just a few years ago at a normative speed of about 600 miles an hour. So we've gone from 6 to 60 to 600. We are on track now, if you take a look at mass mobilization rates, global ranging hypersonic vehicle rates, to enter the next century at about 6,000 miles an hour. I think that's, I'm not saying that plot is destiny, but it makes me think that we're on track to do this, and we probably will do it. The question is, will we be the ones to do it, or somebody else? So that's my pitch, and I'm sticking with it, and I'll be happy at this point to take any comments or questions you all have. And it's been a great pleasure. Thank you all very, very much.
Oh, thank you so much for coming out and giving that wonderful presentation. I learned a lot. Now we're going to open up the floor. If anyone has any questions, feel free to stick around and ask them. If you have to go and do some homework or something, feel free to leave. Thanks for coming out.
You had a quick question, if you don't mind. I want to say, first of all, thank you, Doctor, for speaking with us today. I guess my question would be about what do you think are some of the challenges that face the development of supersonic commercial flight?
It's very interesting you say that. I've been a big fan of it. And the point I'll make is this. We always hear from critics, well, we tried this. We had the Concorde SST, and it was just, it was just a flop. It didn't work. Nobody used it. It was just aging rock stars flying at it and stuff like this. So I got to tell you something funny. If you take a look at the actual operation of the Concorde, it never flew empty. It never, ever flew empty. I was on it once, just experiencing it. Now, it was a subsonic flight in the US from Texas up to Washington. We were cruising at Mach 0.96, which I was pretty impressed with at the time. But anyway, the thing about Concorde is people flew it who had a reason to fly fast. So that if you take a look at the operating model, whether it was the French Concordes or the British Airways Concordes, they were being flown by government couriers. They were being flown by surgeons who were heading off to operations, lawyers for cases, couriers carrying documents, pots, prescriptions, government authorities. You know, during the Gulf War, I was on the air staff in the Gulf War working for Secretary Don Rice, Secretary of the Air Force. And we used Concorde like a business jet. I mean, we always had reasons to blast into the Gulf. And so, because we were about to go to war. And so you had people fly Concorde from Dulles Airport to London, get off the airplane and fly Concorde then from London down to the Gulf. It was that kind of a system, you know. And so when you take a look at this, you realize there is a real market out here for the commercial supersonic bizjet. And, you know, if you take a look at Aerion now, I think they already have a very large number of orders for and commitments for their proposal. There's other companies out there. I think we will see them. The only thing that bothers me, and I don't wish to sound like I'm against the environment because I'm not. I mean, I live in the midst of the environment here and I treasure it. But I'm afraid that we might see the more extreme members of the environmental community do their best to kill it. You know, the idea is going to be, oh my God, you know, it's wasteful. We're going to have NO2 in the upper atmosphere. You know, they're going to dust off all the arguments we heard with the Concorde, which by the way, were largely not true. You know, I took a look at the environmental impact that people were expecting. Oh my God, you know, it's going to put contrails in the sky and clouds will build up and, you know, the world will come to an end. We'll be living in a, you know, we'll be Venus all of a sudden. We'll have a high cloud deck and everything will be picking up and heat and we're all going to melt. You know, no, it's not, you know, it's not the case. The thinking that's going into some of the advanced propulsion systems that we're looking at, and particularly the green fuels that people are looking at for some of these, and then the idea of tailored boom technology, so you're not going to have these very strong, loud, booming problems you had. I was under the SR-71 when it made its last flight from Palmdale to Washington, D.C. The cross-country record that they set, I think, was 57 minutes. It took off at about 4:30 in the morning to the west out of Palmdale. Takeoff was noisy enough. It passed 80 feet over my head in Burma. That was impressive. Climbed out over the Pacific, hit a tanker off Santa Barbara, turned around then and accelerated Mach 3 and came over where we were standing at about 6:30 in the morning at Mach 3.2. And that boom from 82,000 feet really, really got your attention. And you realize, you know, you can't really have this if you're going to have a commercial vehicle. You can't have that kind of noise level over land. The tailored boom technology we're seeing, and there's been some very interesting programs with this that NASA has run, particularly these long, slender approach type vehicles that we're seeing, or some of the others where you've had shorter, stubbier approaches and things like this. We find that we can really reduce the magnitude of that boom. But there's something else as well, and that is if you take a look at city pairs, if you're going to use commercial flight, more typically a commercial supersonic flight, for the most part, you're probably going to be flying from one country to another over a body of water. Now, if I'm flying from the US to Europe, by the time I reach the Bristol Channel or the English Channel, I have to be decelerating to subsonic speed anyway so that I can enter the air traffic network in Northern Europe. But I have 4,000 miles of open water where I can do Mach whatever before I get there. I mean, if I have a hypersonic vehicle, I can go Mach 15 if I want to before I have to decel. It's not going to cause an issue, see? And so I think that's the argument that's eventually people are going to realize that this makes perfect sense. I think it will happen. But the issues that you will face, the challenges you will face will be less technological and more social, political, societal. that'll be the ones that will have to be overcome.
Thank you.
Any other questions or comments?
Does
Well,
anyone else?
I'm going to be sending this paper to Dylan, okay? And I'm going to give you my email address, okay? If you need to get in touch with me. And I'll spell it out. I'll say it and then I'll spell it out. It's floridamockscribe@gmail.com. And the way that is it's FLMACHSCRIBE, that's all one word, lowercase, @gmail.com. And if you have any questions or comments, get in touch anytime.
Okay, thank you very much for that. Once we send out the slides, we'll attach that email. So if anyone has any questions, they'll feel free to reach out to you.
Great, great. It's been a really great pleasure. You've picked a wonderful career field to work in, and I wish you every success.
Thank you again, Doctor.
Yes,
Delighted.
thank you so much.
Thanks so much.